This is an example of how you make a compound from the ions. And zinc sulfide, which is ZNS, comes from zinc plus 2. Zinc is one of the stairs, if you remember back there. And sulfide, which is sulfur with a -2 charge. Sulfur is group 6, 6 minus 8. Sulfide has a -2. All compounds, at least in this section, are going to be neutral. They're not going to have any positives or negatives left over. So +2 zinc combined with -2 sulfide makes perfect. +2 goes to 0. Zinc sulfide is neutral. So compounds need to have an equal number of positive cations and negative anions. And we're going to see you'll have to change the numbers sometimes of the cations or anions to make the compound neutral. But neutrality is the name of the game. In the real world, oxygen and water are all around us all the time, and both oxygen and water will mess with, if you will, the positive and negative ions. We'll talk about this in future lectures. So for right now, the most stable kind of compounds are the ones with neutral charges, and we're going to really try hard in this section to make all the positive charges balance the negative charges.
When sodium and chlorine react, the sodium transfers an electron to the chlorine, forming oppositely charged ions. Although the compound has no net charge, its component ions of opposite charge attract each other to form ionic bonds. In turn, these ions are attracted to others, and an ionic solid called a crystal lattice is created.
When you have table salt, that's positive sodium, group 1A sodium likes to be +1, and chloride, group 7 chlorine, 7 minus 8, chloride likes to be -1. So 1 sodium, 1 chloride come together to make NaCl, table salt. In the real world, though, it's not individual sodiums and chlorines. You actually have a whole bunch of different atoms in together. And that little picture there shows what's called the Ionic Lattice, which is an alternating chlorine, sodium. And the positive, negative charges aren't just like between each atom, they're between all the different atoms. So this distributed positive, negative charges makes a very stable kind of orientation in space. And a lot of crystal structures come from these positives and negatives kind of making really strong pieces with each other. This is another example of that process. This is ammonium chloride. So ammonium polyatomic ion, NH4 with a +1 charge, that's going to need 1 chloride, chlorine 7 minus 8, -1 chloride. So NH4Cl we'll call ammonium chloride. But in the real world, it's alternating. You can see like here's an ammonium, here's an ammonium, and here's an ammonium. And then in between them, you've got these kind of gold chlorides. And they go kind of left and right and up and down and forwards and backwards. Very, very strong interactions. And we're going to see this is pretty important stuff when it comes to making molecules and also sustaining life. These compounds made of positive and negative charges are called ionic compounds, and they're very strong. And the name of the game here is you just want to make sure you have a neutral compound, which means equal positives and negatives. So if you wanted to make calcium with fluoride, which is calcium fluoride. Well, calcium group 2A likes to be +2. Fluorine, which is group 7, 7 minus 8, -1. Fluoride likes to be -1. And to make this compound neutral, you have to have 2 -1 fluorides to balance that +2. You can think about the calcium as wanting to shake hands with both of its hands, but fluoride only has one hand to shake. So you're going to need a second fluoride to make it balance. So calcium fluoride, CaF2. You've got to have the positives balance out the negatives. So you can think about it then almost as having like 2 fluorides to make that CaF2 molecule. molecule. Magnesium is a group 2A metal like calcium, and it likes to be positive 2. And magnesium, a fixed charge metal, always positive 2, which is nice. Now, nitrate is a polyatomic ion. It's NO3 with a negative 1 charge. And polyatomics are just like fluorides above. You've got to have the positives and negatives balance out. And because nitrate has only a negative 1 and magnesium has 2 positive charge, all right, you're going to need 2 nitrates. So magnesium nitrate, which is what happens when magnesium and nitrate come together, you have to have 2 nitrates, 2 negative 1s to balance that positive 2 magnesium. So notice the formula there, Mg parentheses NO3 parentheses 2. If there is more than one polyatomic ion, you can use parentheses like that. Don't use parentheses for anything else, but for more than one polyatomic, parentheses are absolutely cool. So M and G parentheses NO3 parentheses 2 means 2 nitrates for every 1 magnesium. And now you know why that is. Nitrate's negative 1, magnesium's positive 2. Got to have 2 negative 1s to balance that positive 2 charge. Iron is a variable charge metal. All right, earlier we talked about iron plus 2 as iron Roman numeral 2, and we also talked about how iron can be positive 3. So when iron is positive 2 and it reacts with phosphate, which is negative 3, notice here this combination. Again, neutrality is the name of the game. So what I would do is take the 2 and the 3, the charges on the iron and the phosphate, and you can take those two numbers and find the common denominator, which means multiply them together. So 2 times 3 is 6. And if you take that common denominator and divide it by the charge, you've got 6 divided by 2, 3, and 6 divided by the 3 of phosphate, 2. So that tells you that you're going to need 3 irons for every 2 phosphates, or 3 times positive 2 for the iron plus 2 times negative 3 for the phosphate equals 0. And that's a cool way to think about it too. So iron 2 phosphate, which is how you'd write that, 3 irons and 2 phosphates. And again, notice the Roman numeral reflects the charge on the iron, not the number of irons, and that's important. FePO4 would be iron 3 phosphate. You would have an iron plus 3 and a phosphate, which is negative 3. They would come together what I call 1-to-1, positive 3 to negative 3, or 3 minus 3 equals 0. Iron 3 phosphate, quite different than iron 2 phosphate. Just be careful of that. The Roman numerals, super important.